All right, let's get moving. Hey. Okay, guys, can you hear me? Yes or no?
Yeah.
Yes.
Okay, is it clear? Or is it like I'm at a...
It's clear.
All right.
No, it's good.
Okay, cool. Awesome. All right, let's get moving. So levitation, I don't matter. Is that possible?
This Indian seems to float in the air.
All right, so most of you guys will say no, right? You're going to say it's not possible because how do you overcome gravity? Can you levitate without resorting to magic, illusion, technology? Once again, most people say no, and there are people who believe in it, like my dad, obviously. And there's some physicists who believe that sort of stuff is possible. The one that we're focusing on is special hat.
The method of is G, Howard. How are you supposed to meditate if you hit buzzer? How are you doing that? That's pretty cool. How are you doing that? That's pretty cool.
There you have it. You got 15 seconds of levitation. He says, mind over matter. He says, no magic trick. Also says that he learned that in Turkey. It's all about yoga and meditation. Mind over matter. Can you do something like that? Is it possible? All right, guys. So in every single religion, there are anecdotes of those who are saintly being able to levitate. Is there any truth to this? Okay. I'm gonna just volume up from this end because I can barely hear what's going on. All right.
I would like a medium creamy chocolate chip. Yes.
Oh my god, oh my god, oh my god, oh my god, oh my god. This can't really be happening. Babe, you're floating. Oh my god. Oh. Laura, can you hear me? This is really, really freaky. You are like this high off your stool.
It's awesome.
Oh. Laura, can you hear me?
Is this true levitation? What does true levitation actually look like? Does it really look like this? If you could just levitate?
Oh my god. Oh. Laura.
That's impressive. All right, so you got a slight problem. The problem with levitation is you have to kind of overcome gravity. So most of you guys will say you cannot overcome gravity, mind over matter. Is it possible that you're putting too much weight in gravity? Let's check to see. All right, so gravity is not quite well understood, guys. So you got two objects, drop them from the same height, will reach the ground at the same time, right? That's what you got. So the question is why? Why would a heavy object and a light object, when dropped from the same height, will accelerate at the same rate and be able to reach the ground at the same time? How is that even possible? Is it because they both experience the same amount of gravitational pull? All right, guys, that question translates to English. That means, do they weigh the same? No, they don't weigh the same. If they fall at the same rate, how could that be? How could that be that both objects, when dropped from the same height, despite the fact that they don't weigh the same, they don't experience the same amount of gravitational pull, yet they fall at the same rate? How could that be? All right, so that's the mystery. It's one of the biggest mysteries of gravity. So up until Newton came along, no one actually knew how to address that question. Newton, looking at the apple, falling apple, he knew why the apple fell. It was because of gravity. He wanted to know, if objects fall because of gravity, why doesn't the moon also fall from the sky? Well, the first question we must ask ourselves is gravity a force? Now let's check to see if that force really, really extends all the way out to the moon. So is gravity a force? That was a test question. That was a test question on test number 4. And it's kind of weird, but half of you guys actually fumbled it. You're not supposed to be fumbling these questions because we already spent time talking about them, guys. Just about every single question, not just about every single question in the conceptual section of the test has been discussed in length during these lectures, and they're also in the videos. So you should be spending time watching them and digesting that information. You shouldn't be missing these questions. The only thing I'm getting from those of you guys who are not spending time studying the videos or the lectures, you're Googling stuff. The stuff that you're Googling is not what I'm looking for, obviously, because you can only Google information, not understanding. So it's not happening. Is gravity a force? The answer to that question is yes, right? How do we know that it's a force? Because what does a force do? Force causes acceleration. Falling objects, do they accelerate? Absolutely they do. So which means that gravity is a force, right? Because object, like the apple, falling apple accelerates in the direction of the external force. So the falling apple appears to be gravitating towards the earth. That means that the gravity is a force because the falling objects do accelerate. So the next question is, once again, it comes out of Newton. Does gravity extend all the way out to the moon? Now that we established gravity is a force, is it possible that this force extends all the way out to the moon? There are two ways of answering it. One is partially, it's not incorrect. It just provides a partial enough explanation. If gravity didn't extend all the way out to the moon, what would happen? Straight a constant speed away from the earth. Newton's first law. Hence the reason why Newton came up with the law of inertia. Right? Because he wanted to know, is gravity extending all the way out to the moon? What would happen if it didn't? No moon. Right, so the fact that we have a moon, that implies that the force of gravity must be extending all the way out to the moon. But how? The moon is moving at a constant speed. It's moving in a circle. It's accelerating. It's accelerating towards the center of the circle. How's the acceleration? Or force does, by definition, Newton's second law. Right? If something is accelerating, it's accelerating because of the force acting on it. That's what the meaning of it is. And the acceleration is directed towards the center of the circle. So which means that the force is also directed in the same direction. So what do you have at the circle of the stress? What do you have at the center of the circle? The earth itself. So all of a sudden you realize that force that pulls the apple down is also the same force extending all the way out to the moon. Apple falls, accelerates while falling because there's a force acting on it. And it appears to be gravitating towards the earth. That's the reason why it's known as the gravitational force. And the force is also extending all the way out to the moon because if it didn't, what would have happened? The moon would have gone in a straight line at a constant speed. Instead, the moon is moving at a constant speed, but not moving in a straight line. It's accelerating. The circular motion, the acceleration is directed towards the center. If there's acceleration, there's force in the same direction. So which means that the force that pulls the apple down is the same force extending all the way to the moon. Or is it? Why did I immediately turn that into a question? Is it the same force? Really? The reason why I asked that question is because apple falls, moon doesn't, or doesn't. So we have the question of the nature of gravity. So what is the nature of gravity? We need to come up with an expression for the gravitational force. And then we need to check to see if that force really, really extends all the way out to the moon. All right, so if the force of gravity extends all the way out to the moon, how come the moon is not falling? The force of gravity extends all the way out to the moon, how come the astronauts appear weightless? The weight is the amount of gravitational force acting on you. If the weight is the amount of gravitational force acting on you, how is it that the astronauts are weightless, or at least appear weightless? Newton is correct. Just about the only place where you will become weightless, where you can become weightless, almost weightless, is going to be in deep, deep, deep space, which means that you have to be literally millions of light years away from the nearest star or planet. Actually, to be honest with you guys, nowhere in the universe you will be weightless. Absolutely nowhere in the universe. There's no spot in the universe where you will become 100% weightless. Okay. So what is gravity? What is the nature of gravity? It's a force, but we have kind of an explanation as to the nature or details of this force. I don't want to say the nature of this force. So Newton figured it out. He knew that the force of gravity is related to masses. It's going to be related to the product of the masses. Product means multiplication. The bigger the product is, the larger the force is. Then he realized that the force is going to diminish with distance. The radial distance between the masses. The distance is going to be measured with respect to the centers of mass. All right, so further away these masses are, the smaller the force is, the closer they are, the larger the force will be. And then he made a correction. He said the force is going to diminish with the square of the distance. This is known as inverse square law. All right, so it's going to diminish with the square of the distance. All right, so when you take the proportionalities and turn them into an equation, you have to have a proportionality constant. proportionality constant in this case is known as capital G, which represents the strength of the gravitational force. All right, so capital G is going to represent the strength of the gravitational force, otherwise known as the universal gravitational constant. Universal gravitational constant. That's what it is. All right, so going back to the question that we had, falling objects do fall at a constant rate, right? The rate at which they're falling is roughly about 10. Actual number is 9.8. All right, so in the absence of air friction, in a vacuum, all objects, regardless of their weights, regardless of their sizes, everything is going to fall at a constant rate. Rate at which they will fall to the surface of the Earth is going to be 9.8. All right, so the question is why? The question is why? Why is it that the mass doesn't matter? Why is it that the mass of a falling object doesn't matter? All right, so how come everything is falling at this rate because of their masses, because of their weights? Newton's explanation was kind of elegant. It says that the weight is caused by the gravitational force. Here's your weight, here's the force of gravity. All right. Our force of gravity is mass of the Earth. Small mass is the mass of the apple. R is the distance between the apple and the Earth. We're thinking there's not much of a distance here. You're completely missing the point, guys. The distances are measured with respect to the centers of mass. All right, so weight is given by the gravitational force. So you have to equate both sides. First, that the mass of the apple is going to cancel. So the mass of a falling object doesn't matter because it's just going to cancel out of the equation. And R is going to represent distance, the radial distance between the centers of mass of the apple and the center mass of the Earth. For all practical purposes, this is going to be the radius of the Earth itself. All right, so come up with a mathematical expression that makes some predictions. How fast objects fall will depend on the mass of the planet. It's going to depend on the size of the planet. It's going to be inversely related to the size of the planet. So the initial value for gravitational acceleration is going to be 9.8 meters per second squared. 9.8 meters per second squared. So that's what we got moving forward. So what is the theoretical number? So we have to, this is the formula that Newton came up with. Capital G is the strength of gravity. It's really weak, 10 to the minus 11. It means that there are 10 zeros in front of it. This is the mass of the Earth. What is the radius of the Earth? G is the acceleration due to gravity at the surface of the Earth. And the measured value is going to be 9.8. The theoretical number is also 9.8. Notice that the theoretical predicted value as well as the measured value, predicted as well as the measured values match. If the experimental and the theoretical numbers match, which means that the theory is good.